is a local extrema. Remember that very first example? We had absolute extrema, but not local extrema. So the EBT guarantees the existence of absolute extrema, but not local. We did not have local extrema in that first example where the EBT did apply. Questions? Questions? Yeah?
So it doesn't have to be closed to
Well, here's the thing. Because this is not closed, the theorem did not apply, which means that we just have to figure it out on our own. Okay. We could have it, and here we do. But we have to figure it out by ourselves. That's all. The theorem didn't guarantee anything. The theorem didn't apply. Okay. A theorem that does not apply cannot guarantee anything. All right. Okay. Questions? Questions? Okay. So, individually, it's not that these are mind-blowing, but they're all these little subtleties, I mean, so you have to get practice with these ideas. All right. Any questions? Any questions? Well, we're going to ask the question, how do we find extrema? And let's start with local extrema. Okay, then later on we'll talk about absolute extrema. Like I said, calculus more directly deals with local behaviors, right? And then we have to look a bit more widely in order to capture absolute extrema. All right, let's start with local extrema. Where are candidates for local max and min points? Here we go. All right. Issue C. Where do we look for local max and min points? We call these critical numbers, and we're going to use this term a lot. CNs, critical numbers. Okay, that's the last time I'm going to write critical numbers. From now on, CNs. Bear in mind, in pre-calculus, they might have used this term in a different way. All right. Now, what does the theorem here say? If a function f, has a local maximum or local minimum at x equals c, where c is a real number. Okay, if we have a local max or min at x equals c, then what must be true about the derivative? Now remember, folks, I and many books, maybe not Swakowski, but I and many books say that we at least need continuity. It has to be defined there. Okay, there literally has to be a point. Everybody agrees on that. You have to have a point there, right? You have to be defined there. Most books would agree we would need continuity also, all right, at C. Well, if we have a derivative, what number would that derivative have to be? 0. Okay, then f prime of C equals 0. So, for example, let's say we have a graph going like this, right? Like a parabola, for example, right? Here's a local max point. Maybe it's an absolute max point, in fact. We have a horizontal tangent line. We've got like this, right? Okay, turning point, right? Basically turning points. We want to locate turning points. You can think of local max and min points as turning points, which is why if you don't have any neighborhoods to your left or to your right, you're not really turning, right? Okay. Or if we have a local extremum at x equals c, either there is a derivative and it's 0, or f prime is what? Yeah, f prime at c does not exist. Or is undefined. D and E and undefined mean the same thing. All right? So, the only way you can have a local extremum, okay, if you have a local extremum, then either the derivative is 0 there, or it's undefined. Like in that absolute value, that corner thing, or maybe it's a cusp thing, right? X to 2/3. Right? 0, the derivative has to be 0 or D and E at a local extremum, right? However, what about the converse? The converse goes like this. If the derivative is 0 or D and E, do we have to have a turning point? Do we have to have a turning point where the derivative is 0? No. Give me an example where you have a 0 derivative, but the graph's not turning around. How about the graph of y equals x to the third? Y equals x to the third. Consider f of x equals x to the third. All right? We have a 0 derivative at 0, at x equals 0, right? We have a horizontal tangent line. Okay, if your derivative is 0, that means you have a horizontal tangent line. All right? Is the graph turning around? No, no. not turning around. This is not a local extrema. Okay, this has no extrema whatsoever. It has no extrema whatsoever. The converse does not hold. Okay, just because you have a zero or undefined derivative does not necessarily mean that you have a turning point. Okay, so be aware of that. This is our classic counterexample of that. Okay, so be aware that this is a case where you have no extrema. All right. So the converse does not hold. Okay, just because an if-then statement might be true does not necessarily mean the converse must be true. Okay. You know, like I like to say in pre-count, you might agree with the statement if Pat is a daddy, then Pat is a man. Okay. If Pat is a daddy, then Pat is a man. It does not necessarily follow that just because Pat is a man, that Pat is a daddy. Otherwise, guys like me, we might have some surprises from Barney, right? You are the father. Okay. All right. So how do we define a critical number? All right. The critical numbers of F are all numbers in, well, first of all, you literally have to have a point there, right? They're all numbers in the what of F? The domain of F, okay? All numbers in the domain of F, okay? Where F prime is either what or what? Zero or d. Okay, so that's important. The critical numbers of F are the only numbers, are all the numbers in the domain of F. And don't forget that. They have to be in the domain. There has to literally be a point there. Or F prime is either 0 or DNE. Okay, now by the way, some of you might be going, well shouldn't we have some sort of continuity condition? Now bear in mind, you know, we don't always have local extrema at critical numbers. So we don't need a continuity condition here. And in fact, we're not going to put one on there. Okay? So if I ask for critical numbers, then we're not going to require continuity. Okay? Now that'll help with the local extrema issue, but you don't have to have continuity at critical numbers. Right? You have to define that, but you don't have to have continuity. Okay? And clearly, you don't have to have differentiability. Right? In fact, if you lose differentiability, we're actually interested in right, like over here or over here. If you lose differentiability, then we're actually kind of interested in right? But again, here we don't require any continuity conditions. Okay. Now, why do we care about CS? These are the only places where we can find what for L. These are the only places where we can find what? What kind of maximum and minimum? Local. Now, absolute, you might have different things going on. But why do we care? Okay, CNs, they're like candidates. These are the only places, or candidates, you could say. These are the only places or candidates for X or whatever, right? Where F can have local extrema, maxima or minima. Critical numbers are the only places or candidates where F can possibly have local extrema, meaning maxima or minima. Must F have a local extrema at a critical number? Do we have to have? No. And the classic example is the X cube example. Okay. So when I say can here, okay, it's not must. It's very legalistic here. Okay. F can have local extrema at critical numbers. It doesn't have to though. But they're the only places where you can have them. You cannot have a local extremum as something that's not a critical number. That's why if we have a function and we want to optimize it, we like looking for critical numbers because those are the only candidates for local extrema. All right. Bear in mind, continuity doesn't come an issue there. All right. Questions so far? Questions so far? I'm just going to do the next part of part D. Okay. Then we'll take the break, and then I'm sure that you'll have questions afterwards.
I also do that. And then I finish the
you know how if you have a presidential election, right?
Yeah.
The only person who can be president someone who runs for president, someone who's a candidate.
Yeah.
Right? It's not like Chavez in Venezuela. You can't say I'm president now.
So I know the word, but how it does it relate to it?
Yeah, meaning, if you're looking for local extrema, right? Local maxima and local minima, where do you look? Okay? You're only going to look at the values for x where it's possible that you might have a local maximum or minimum. The critical numbers are the only places where it's even possible. Okay? So in other words, it's necessary. In order to have a local maximum or minimum where you are, it's necessary that you be a critical number. Okay? Yes. Okay, it's necessary that you be a critical number, all right? But it's not sufficient. It's not sufficient because you might be a critical number, like here, 0 is a critical number, but you don't have a local extremum, okay? But if you are turning around, like here, you have to have a CM here. This has to be a CM, a critical number. This has to be a CM. This has to be a CM. This has to be a CM. Anytime you have a turning point, you have to have a CM here.
So there's both local max and the absolute max.
Okay, now that's a different issue. That's a different issue. Some local maxima are also absolute maxima, but not all. Okay? And we'll talk more about that. Okay. Right now we're doing local. We're just doing local. Okay? So remember, critical numbers are where we look for local extrema. Bear in mind, we don't always find any. And not all the CN will correspond to local extrema. Right now we're talking local. Okay, the whole local absolute relationship, that's a bit more subtle. We'll talk about that. Questions? Remember that earlier example where I had that like hook and it stopped? There, we had an absolute extrema, but it wasn't local. So not all absolute extrema are local. Not all local extrema are absolute. Okay? Okay? All right? Again, not all absolute extrema are local extrema. Not all local extrema are absolute extrema. Okay? So, either way. Questions? Anything else? Questions? All right, let's do an example, and let's look for absolute extrema. All right, we're going to apply the EBT now. All right, part D, and this will be my last. Okay, this will be my last part before we break. Okay, it's not break down to tears, but all right. Okay, well, bottom line, we're going to apply the EBT. That's the bottom line. We're going to apply the EBT. Alright? So here's our task. We're going to find absolute maxima and absolute minima of a function f on a closed interval from a to b. We assume a is less than b. Alright. Find the absolute maxima and minimum of a function on the closed interval. We're going to assume that f is continuous on said closed interval. All right. Okay, so assume f is, what's that key word? Continuous on that closed interval. If the function is continuous on that closed interval, what theorem applies? The EBT, the extreme value theorem, guaranteeing the existence of absolute extreme values. All right. That means the EBT applies. And if the EBT applies, that means that these, what's that big philosophical E word, or backwards E? They exist. It says that these guys exist. They exist. Okay, meaning the absolute maximum and minima of the function on that interval. Now remember, we're talking in context. This is all in the context of that restricted domain. We don't care about anything that's happening outside of that interval. Okay? So don't go, well, if we take the graph further, no, we're not taking the graph beyond that restricted domain. Okay? So no what ifs. Okay, like that 1 over x guy, I don't care that he went up further if you were to go on. There is no what if. Alright. So if EBT applies, we're guaranteed the existence of absolute maxima and minima of the function in context. Okay, that's the restricted domain. We don't care about anything outside. Okay? So where are our candidates? Candidates for absolute maxima and minima, meaning the x-coordinates. Well, we're looking for absolute maximum and minimum. Where can we get Where are the x values where we can get the highest function values? Well, where would we look? Okay, critical numbers. Why would you look at critical numbers? Because those are the only places where we might find what? The local. So wouldn't you agree? Look, folks, not every local extremum is an absolute extremum. But wouldn't you agree? It's a nice place to look, right? Okay. I mean, it's like a murder mystery. The husband's right there, right? Okay, so yeah. All right. So the candidates are local maxima and minima. All right. Which means that we might want to gather all the critical numbers. Okay, local maxima and minima. More generally, critical numbers. Okay. More generally, critical numbers. Okay. Now, bear in mind, we're going to start by collecting critical numbers. And, you know, right off the bat, we might not know which ones are local, maxima, or minima, but the bottom line is we're going to find critical numbers, okay? The idea being that some of them might be local, maxima, and minima. Right. I mean, you might have a situation like this, okay, where, okay, here's a local minimum point. Here's a local maximum point. Now, this will also correspond to a critical number, but that's neither. Okay, fine. He's not interested. He's just a guy. He's like a pit stop. Fine. More generally, CNs. But here's the thing. If you remember our previous examples, aside from local max and min points, there were some other kinds of points where we could find absolute max and min points that weren't necessarily turning points.
The endpoints.
The endpoints. Okay, like that hook example. Also, endpoints. Okay, these guys add endpoints. Okay, I showed you some examples, right? Like 1 over x, a, b. Oh, come on. Okay, there. You know, if you think of any linear function, for example, right? If you take any linear function and truncate it, right? Then you know your absolute extrema will take place at the endpoints a and b. All right. Maybe your absolute max point is an endpoint. Maybe your absolute min point is a local guy. That can happen too. Sure. Okay. But you agree, these are the candidates, right? Local max and min points. The CNs would help a lot, right? And also endpoints. Okay. So make sure that we also check these guys out. Okay. So it's like an Easter egg hunt, right? I mean, where do you look? Okay. You look at the critical numbers. You look at a and b. That's the bottom line. Okay, so what are the steps? I'm just going to reiterate the steps in my notes. Okay, steps. The first step is to find the critical numbers. Yep. Steps. How do we find absolute maximum and minimum on a closed interval if we have continuity? Bear in mind, if you don't have continuity, then if you have like a VA or something, then it'll be harder. Okay. Number 1, find all critical numbers. Open interval from A to B. Now, if you put the closed interval, I will not be deeply offended. But the thing is, technically, we're finding CNs to find local extrema, and we're not going to find local extrema at endpoints. That's why we have parentheses. If you put closed brackets, I won't be profoundly offended by that. Right. And in fact, you can have critical numbers at A and B. It's just that you can't have local extrema there. Okay, but find all critical numbers in open A B. Second, all right. Well, it's like a. Oh, we're going to get.
Can you repeat that last phrase that you said? You said you can't have.
Oh, the part I mumbled. Okay. Okay. Technically, from definition, it's possible to have a critical number at the endpoints, at A and or at B, but you just cannot have local extrema there. You can't have a local maximum endpoint there. So if you do have critical numbers here or here, you can't have a local extremum there, but you can have an absolute extremum. So all these little nooks and crannies. But bottom line, if you put brackets there, I won't be offended. The reason why I put parentheses is that for now, we're looking for local extremum. That's what it's going to be a beauty pageant. All right. Although it's kind of a funny beauty pageant. We're going to crown the most beautiful and also the ugliest. Okay, would that be interesting? Can you imagine all these people women coming out, one of them's ugliest, the other one's ugliest. All right. All right. Yeah, she missed humility. All right. Evaluate f of c for each critical number C in that open interval. Bear in mind, if you get tentative critical numbers outside the interval, they're not technically critical numbers. Remember, critical numbers have to be in the what of the function? In the domain. Okay, so as far as we're concerned, this is a restricted domain. Okay, so when we work out critical numbers, don't take any numbers outside that restricted domain. But anyway, it's a beauty pageant. We evaluate the function value, f of c, for each of the critical numbers c in that open interval. All right. Third. Well, okay, go ahead.
When you say value, you mean find the derivatives?
No, we're just doing function. The derivative stuff, that's wrapped up in here, right?
Okay.
Okay, we use derivatives to find the CNs in the first place. Here, it's a pure beauty pageant. Plug into the Big Daddy.
Okay.
What's your y coordinate? Ultimately, that's your score, your pageant score. What's your y coordinate? Okay. And we hear about the highest y coordinates and the lowest ones. Okay. Anything else? Anything else? Where else might we have now? This should take care of local stuff, but we'll be able to identify local extrema. But where else can we find absolute extrema? Where else can we find it? At the inputs A and B. So we have to evaluate f of A and f of B, because they're thrown into the pot. Okay? Where did we go? Okay, they're in the mix too. Okay, maybe it's the Donald Trump's daughters. Okay. Okay, so we have to evaluate f of A and f of B. Okay, maybe A is Ivanka Trump, maybe B is Donald Trump Jr. the wig. All right. Maybe he already has a wig. Okay, so those are the endpoint values. All right, number 4. Run the beauty pageant. Okay, so I'm going to use that word candidates again. Okay, among the candidates from steps 2 and 3, okay, well, the highest function value is going to correspond to the absolute max, the lowest with the absolute min. All right. Okay, so the highest, I'll stress f value, the function value, right? The highest f value is the absolute maximum value. Okay, in context on that closed interval. Okay, and right, the lowest f value is the absolute min value on the interval. All right. So it's a beauty pageant. We crown the most beautiful and the ugliest. Right. Like the ugliest man contest in Colombia. And the guy was smiling too. He was proud to win. Ugliest man in Colombia. Maybe the ugliest man in Colombia gets the most beautiful woman in Colombia. Alright. Okay. Alright. Let's do it. Example. Really a table will work for these last steps. Alright, here's the task. Find. Okay. Now, right now, we don't have the means by which to classify local extrema right now. We'll do that later. But we can classify absolute extrema. For now, it's actually easier to classify absolute extrema. Right? Find the absolute extrema. Okay. Because the whole idea of, identifying local max and min, that's going to be later. But, okay, find the absolute extrema of f where f of x equals x to 1/3 minus x plus 4 on the closed interval from -1 to 8. And as you can see, I didn't want to make life too easy on you. That is not a polynomial, unfortunately. He is algebraic, he's not that bad, but I didn't want to make life that easy for you. Okay? Find the absolute extrema of f where f of x is x to 1/3 minus x plus 4 on that closed interval from -1 to 8. As far as we're concerned, that's the restricted domain. Alright, so you see what we're looking for here. Alright. One comment, by the way. You agree this guy is continuous, right? This is a cubic, right? This guy's continuous. that interval, right? So observe that f is continuous on the closed interval. Therefore, what theorem applies? EVT. Okay, so it's the IVT, but it's EVT here, right? The EVT applies. Okay, meaning that we're guaranteed to have an absolute maximum and an absolute minimum somewhere in here in the context of that interval, right? In the context of that restricted domain. Okay. So, let's find them. All right. First of all, and here's the hard part, find all the CNs in the open interval. All right. That's the hardest part. Find all the CNs. What's a CN? It's a critical number. These are candidates for finding local extrema. All right. But in fact, we don't have to identify who's a local max versus local min. We're just going to put all these candidates together. Question? All right. Okay, so let's find the critical numbers. Number one. Okay, find the critical numbers in the open interval from -1 to 8. And as I mentioned before, f could have critical numbers at -1 and 8 themselves, but we're going to check those places anyway. All right, find the CNs in the open interval from -1 to 8. All right, and we agree f is defined and continuous all throughout. All right. So, where are the critical numbers? Okay, well, they're numbers in the restricted domain, or they're numbers in there. Okay, I want the numbers in here, where the what is what or what? Where the derivative is 0 or any. Okay, so find where f prime is 0 or d any. Okay, and you can pick your order. I'm first interested where it's d any first. Okay, well, let's work out the derivative. We have this guy. What is f prime of x? All right, term by term, what's the derivative of x to the 1/3? 1/3 x to the -2/3. And then? -1. I sound like, dude, where's my car? And then? What's the derivative of 4? 0. Okay, so there's our derivative. You know what? It might be in your best interest to, kind of play with this thing, see if we can make heads or tails out of it. All right. First of all, how can I rewrite this? 1 over 3 x to the 2/3 -1. Okay. I do know one thing. I do know that there's only one value of x for which that's undefined. What value? 0. Okay. So observe that f prime is d any. Okay, only at x equals 0, inside this interval, right? F prime is d any only at x equals 0, because obviously we have a problem if we're dividing by 0 here, right? And that's sufficient to demonstrate non-differentiability. Bear in mind, we have basically a square here and a cube root down here, okay? The cube root is cool with negative numbers, okay, so that's okay. The only problem with 0 is it's not in it. Which all agree, f prime is only d any among these numbers here, right? F prime is d any only at x equals 0, among those numbers there. All right? In fact, even if we're extended. Now I want to know where the derivative is what? 0. Where the derivative itself is 0. Let's solve that. All right. So, we have to solve the following equation. Let's solve f prime of x equals 0 on this open interval. Okay, remember, if you get like 10 or something, you throw it out. We don't care. All right. Okay, so where's this thing equal to 0? 1 over 3x to the 2/3 minus 1 equals 0. Add 1 to both sides. 1 over 3x to the 2/3 equals 1. Right? We're going to assume for now that x is not 0. Okay? Assume for now that x is not 0. Because we're already taking 0 out. Okay? I can take the reciprocal of both sides. Right? Take the reciprocal of both sides. I get 3x to the 2/3 equals 1. You can take the reciprocal of both sides. Or you can multiply both sides by this. 3x to the 2/3 equals 1. Okay? Divide by 3. X to is 1/3. That's your algebra. And I just kind of mentioned this, all right? When you raise something to the 2/3 power, what are you doing? So you're taking the cube root of x, right? And then squaring it, which way? I'll do this, okay? X to 2/3, it's the cube root of x squared, all agree? Cube root of x squared. That's 1/3. All right. How can I get rid of the cube? Cube both sides. Cube both sides. That's clean, you don't have to check. Okay, cubing is better than squaring, because squaring means you have to check. Alright, so we cube both sides. Okay, we don't have to check, this is clean. Alright, okay, what's the cube of the cube root of x squared? X squared clean equals, what's the cube of 1/3? 127. Alright. Question so far. Question so far. So x equals what? Plus or minus square root of 1/27. And if you want, you could rationalize that, but I'm not even going to bother with that. I'll just say this is about plus or minus 0.192. Okay, so I'll just approximate this one. Okay, so what are our... Oh, and by the way, I should check something here. All right. You agree these are both numbers in that interval, right? These are both in the interval from -1 to 8. Check. Check that. Because if we had like plus or minus 10, we have to knock them out. All right. So what are our three critical numbers here? Our critical numbers are 0 and about 0.192 and about negative 0.192. And for now, we can go ahead and use those approximations. We have 3 CNs. And they're all in the open interval. Questions?
How do we get from the second step to one left
Here?
behind you?
Here? Or here?
Behind you. So from the second one, 1/3x to the 2/3 equals 1 to the next step.
You can either take the reciprocal of both sides. The reciprocal of this is that. The reciprocal of 1 is 1.
Okay.
Or you could multiply both sides by the denominator. 1 equals 3 to 2/3, then turn around. Either way.
Thank you.
And we can assume for now x is not 0. We already know 0 is an issue, right? So we can assume x is not 0 for now.
Thank you.
Okay, well, any questions? Any questions? Because of course the derivative cannot be d and e and 0 at the same time. So once you take care of these cases, you can assume, you can exclude those cases from that analysis. Questions? We have our 3 candidates. Let's run our beauty pageant. Oh, wait. They're not on one side. Also, who are other candidates? -1 and 8. Don't forget the trumps. Ivanka and Don Jr. to wait. So we actually have 5 candidates. We have 5 candidates. We have 3 candidates for local extrema, all right, in there. But 5 candidates for absolute extrema. Okay. I don't even know if we have local extrema. I know we must have absolute extrema because of what theorem? The EVT. By the EVT, we're guaranteed absolute extrema, not necessarily local. All right. Let's run our beauty contest. So steps 2 through 4. It's all in the big old table. All right. So here are our candidates. Okay. So our candidates for x. Okay. We always start with a, which is negative. I mean, you don't have to do them in order, right? But the lowest value will always be a. Okay. Then in order, it's going to be 0. And then, oh no. It's this guy. Negative. About negative 0.192. Technically that's next. And then 0. And then about positive 0.192. Okay. And then the last guy, the greatest guy is always b. B is 8. Okay. So we have these 3 CNs, and we have the 2 endpoints. All right. So -1, negative 0.192, 0, positive 0.192, and 8. All right. Those are 5 candidates. Okay. And there they are in their bikinis, and all right. Fine. Okay. What are their ratings? F of x. Okay. Now just to remind you, where do I plug these numbers in? The big A, right? The original guy I gave you. So just as an example, okay, I'll remind you, this was x to 1/3 minus x plus 4. I'll do this once. Okay, so for -1, okay, f of -1 is going to be -1 to the 1/3. Well, the cube root is -1, that's fine. Minus -1, and then plus 4. That's just 4. Okay, so the function value there is +4. All right. And then I'll just go ahead and list the various others. Okay, so we have 4 over here, all right. And then over here, we have about 3.615. Okay, so f of this is about 3.615. F of 0 is 4 also. But will the time matter? We don't know yet. How about f of positive 0.192? That's about 4.385. Maybe it won't matter. In fact, at this point, I know that the 4's here are not going to be absolute extremas, so they're out. Okay? Because we have guys who are lower and higher. Okay, how about f of 8? That turns out to be -2. Which is kind of mean. We're saying that this poor person is a -2. Okay. Well, I guess that person wins in a certain sense. All right, questions. Okay, those are our scores. Those are our 5 scores, the function values, the y-coordinates. All right, well, let's compare. Okay, let's start with the most beautiful. We ask that the witch's mirror, right? Okay, so which is the most beautiful? Which row here? Row 4. All right, so it looks like we have an absolute max point in context, right? The absolute max point on the interval, okay, is given by about, all right, about, and you can always use the squiggle towards appropriate. About what? 0.192, right? About 0.192, comma 4.385. About 4.385. Okay, that point wins the crown as most beautiful. What point wins the crown for most ugly? Who's most ugly? 8, -2. 8, -2. All right. Okay. And I'm likely to ask for absolute max points and absolute min points, because then there's no ambiguity. I want both the coordinates, I want the x and the y. All right. Questions?
It's approximate because you round it.
Yeah, because around. Yeah, I read it right here. You could work it out exactly, but questions? Let me grab this thing, and then that'll be it for now. And then after this, you can do all of 4.1, number 1. Yay. What is that, ABC or something? That's ABC. It is ABC. Yeah. All right. Okay. Let's look at the graph of this thing. What does it look like? Okay. Again, you don't know all the information here. You can make guesses. You can guess. I mean, we're relying on the notion that this guy's a fairly, he's not too complicated. He's not that bad. He's not polynomial. He's not that bad either. Okay. So here's what's happening, and you can see why it makes sense. You can at least see why it makes sense. All right. X, Y, not to scale. All right. Okay. Let's put the -1 over here. The 8's way over here. Okay. Not to scale. Okay, we have -0.192, we have 0, we have positive 0.192, about. All right. Well, again, I'm just kind of sketching this out. Okay. So we start with -1, comma 4. All right. And then we dip down, okay, to this guy here, and that's about 3.6, right? About 3.6. And then we go back up. Okay, by the way, it turns out we do get a local midpoint there with a horizontal tangent line. Okay, remember the derivative was 0 here, right? Then we go up to here. Okay, and then up to the winner, which is this point up here. Okay, that was the absolute max point. By the way, if I draw this correctly, what happens over here? Why was this guy kind of? Okay, yeah, he's a y-intercept, but why else is he interesting? Yeah, F prime was DNE. What happens here? There's not a hole. What's the tangent line there? It'll be vertical. Yeah, if I draw this right. Remember the cube root function, right? It's a lazy snake, and you have that steepness, that steep vertical tangent line. we have a vertical tangent line at the y-intercept at 0, 4. Okay, so yeah, it's that lazy snake behavior. We have a vertical tangent line. Okay. Otherwise, he's not an extremum of any sort. Okay. So this is neither. This is a local midpoint. This is neither, although we do get a vertical tangent line. That is a local and absolute max point. All right. And then whoosh. Oh, no, there's a -2, doesn't it? Yeah, put it over there. Whoosh. All right. And that's our absolute midpoint, but it's not a local midpoint. It has no neighbors over here that we care about. All right. So it makes sense. If I show you the graph, it makes sense. Okay. Questions? In this case, our absolute midpoint was at an endpoint, and our absolute max point was actually at a critical number. It was, in fact, a local max point as well. All right. Question.
I'm trying to think again how a key at any point could have been a...
You could have a vertical tangent line. You can have a corner or cusp. You can still have continuity. You can still have defined continuity. Okay. But if the derivative is undefined, it means you might have a vertical tangent line, corner.
Yeah, but how would that be a max point if it's DNA?
Oh, okay. Is it possible that...
Because I'm just trying to think again.
Oh, yeah, if you have a cusp. Yeah, if you have a cusp.
Oh, that's right.
Then it's possible this could be an absolute max.
Okay.
Yeah, that's okay. Yeah. Various things can happen. Okay, even with continuity. Even though we have continuity, still we can have some weird things going on. But not too weird. Question. And again, we're going to talk more about classifying these kinds of points later on. Maybe using local behaviors and derivative information. Okay. Again, you go through the first section, number 1. And we'll talk more about this. We'll finish this up after this. All right. It was a late break, but if you've mastered the whole book, you don't have to come back, but it would help if you do. You know, and if you come back, you know, if you stick around the study sessions, it might help you out at the end, right? I might remember you and go, that person stuck around. Although I won't hate you or, you know, actively penalize you. Go see now. All right, questions? Any questions about what's happening Wednesday, right? You're giving the homework, right? Give the homework, you're going to take the test. I think I'm allotting an hour and a half for it, like last time. 10-minute break, at least a 10-minute break for everyone, and I'll finish 4-1. All right? Questions? You don't have the homework?
Is it 100 out of the points 105?
Once again, 105 possible. Question, we need the homework. Yeah.
Just on the test, so like if we just didn't show our work but gave you the right answer, like we did our work.
Depends on the problem. I might say show work. Well, I mean, basically, try to show work.
Because my work killed me on like, it hurt me more than it would help me on my test.
If there's an outright contradiction, there's a problem.
Yeah, well, say I would get the right answer, but then some of the steps I might like, you know, I might just put a little negative here, but I got the right answer still, but I lost more.
Well, again, if it can be construed as a contradiction, where you're giving me like 2 answers, you know, then that can be problematic. Actually, if it's what I think you're saying, I needed that work anyway.
Okay.
Yeah, I needed. It's that kind of VA type. It's like it's a limited video negative.
Yeah.
Right? Yeah, I think that's one where maybe you wrote the wrong sign, and I graded on that. I did grade partly on that.
Yeah.
So no, you want to show work.
Okay.
If you had given an answer early, you would have gotten maybe a couple points out of 6. So no, you want to show the work.
Okay.
Just make sure you're not contradicting yourself. Okay.
Are there any difficulties in the grade that you get at the homework?
Will the test be the same level as the homework?
But I have heard him doing homework. So
Anything on the homework's fair. So I can make one part easier, one part harder. Anything can happen.